Hi everyone, my name is Eoin. I'm a final year PhD candidate at the University of Leeds, and I'm going to talk a little bit about the geodetic study of magmatic systems, specifically how shared magma dynamics have caused correlated displacement at Galápagos Volcanoes. This is work that I've done with Susie Ebmeyer up in Leeds, funded by European Space Agency as part of COMET. So, I'm looking at the Western Galápagos. These are two islands of Isabella and Fernandina, located in the East Pacific that straddle the equator. There are 6 major volcanoes here that we look at. Going from north to south is Wolf, Darwin, Fernandina, Alcedo, Sierra Negra, and Cerro Azul. These volcanoes are very volcanically active. There have been 6 eruptions there since 2015, most recently at Wolf last January, which produced these lovely lava flows on the southeastern flank of the volcano. In addition to the high levels of extrusive volcanism, there's also a high degree of ground deformation. So this is a map of cumulative displacement in the ascending track direction that we constructed using Sentinel-1 INSAR from 2017 to 2022. This is leveraging the LIGSAR stuff that Juliette was talking about the other day. And the key takeaway when you're looking at this map is that anywhere we see these fringes, so especially at Fernandina, Cerro Azul, Sierra Negra and Wolf, there's been a lot of ground deformation. This has been rewrapped 10 centimeters of displacement. We also see some at Darwin and Alcedo, though it's much lower magnitude in this kind of presentation. So with this data set, we produced time series of deformation, again, going from 2017 to 2022. In these plots, we have displacement between the satellite and the ground, given in millimeters on the y-axis. Date is on the x-axis, and then the vertical lines show when there's been a major eruption or a major unrest event. The top row shows the reference pixel, so that's the point that all of the displacement is relative to, and then we have the time series for the individual volcanoes themselves in the subsequent rows. So we produced our time series, and then we started to see some quite interesting trends. We started to see simultaneous changes at multiple volcanoes, at spatially distinct volcanoes at the same time. So to draw your attention to a few of these examples, if we compare the time series for Sierra Negra and Fernandina, again with displacement in millimeters on the y-axis, we can see that following the 2017 eruption at Fernandina, at this yellow arrow, there was an uptick in the uplift rate at Sierra Negra at the same time. Similarly, if we again compare Fernandina, this time with Alcedo, you can see that Alcedo, which has been undergoing long-term subsidence due to the crystallization of its subvolcanic reservoir, it switched to uplift for a short period. This period of uplift coincided with this uptick in deformation rate at Fernandina, and it ended just prior to the 2020 eruption of Fernandina. And finally, if we compare again Fernandina to Cerro Azul, we see that just prior to the 2022 eruption of Cerro Azul of Wolf, there was an uptick in the deformation rate at Cerro Azul, which coincided with a pause in the uplift rate at Fernandina. These observations that we've made are complemented by previous observations of correlated deformation that Scott Baker made in his 2012 PhD thesis. He noticed 4 periods of correlated deformation between 2006 and 2011, initially with correlated deformation and seismicity between Darwin, Alcedo and Fernandina, followed by correlated deformation during the 2009 eruption of Fernandina. So if we look, we can see that during the eruption, the uplift rate at Wolf tapered off, where the uplift that had been ongoing at Alcedo stopped and indeed switched to subsidence. Following this, during a period of unrest at Alcedo in 2010, the uplift rate of Fernandina slowed, and during the 2008 eruption of Cerro Azul, the uplift rate at Sierra Negra slowed down a bit. So in total, we have observations of correlated displacements at every Galápagos volcano, well, of the important ones, over 16 years. Our question then is, what is causing these correlations in neighboring volcanic time series? First thought, it could be something that we were introducing ourselves through our processing choices. So for example, choice of reference pixel. However, we plotted multiple reference pixels from around the islands and found that regardless of what we plotted, the general trends that we were seeing were the same. Some of you who may be familiar with INSAR may know that they're very vulnerable to interference from atmospheric noise that can kind of give you apparent deformation where there isn't any. However, we applied atmospheric corrections using the GACO service to remove, or to at least minimize these impacts, and we're confident that it's not due to an atmospheric component. We then thought maybe there's shallow connectivity, as in the upper 10 kilometers of the crust, where we can see with INSAR between these volcanoes. However, as I showed earlier, in the Galápagos, lateral intrusions are quite common, but when they occur, they're also very obvious. So if we look at, again, Fernandina, Cervosol, and Sierra Negra, it's really obvious that these intrusions have occurred. There's really no evidence between any of the volcanoes of any sort of shallow connectivity. So to try and test this a bit more, we started to perform some analysis on our time series. The first thing we did was to try and see when these periods of heightened correlation were occurring, which we did using windowed correlation analysis. So we calculated the correlation coefficient, so the strength of the linear relationship between two variables. Like if we plot one time series on the x-axis and another on the y-axis, they're perfectly correlated. It would just be a straight linear regression. We broke each time series into windows of this size, calculated this correlation coefficient, and then just iterated that across our pair of time series, the same way you calculate a rolling average, except calculate correlation coefficient. This is done pairwise. So in this plot, each row shows the strength of the correlation coefficient, blue being negative, red being positive, between each pair of time series. So for Alcedo Sierra Negra, Cervosol, and so forth, the whole way down. And what we can see generally is that when we see a lot of these correlations, so when lots of time series have strong correlation coefficients, they occur during periods of heightened volcanic activity, which is, it makes sense. During the 2018 eruption at Sierra Negra and Fernandina, we see this band of correlation here. Just prior to 2022 eruption at Wolf, we see this band. Then also here coincides with an uplift period at Darwin, and here with that uplift I talked about at Alcedo earlier. We then did further analysis. We performed independent component analysis, which is a blind signal separation technique that allows us to extract independent components from a mixed signal by maximizing their independence. We performed this analysis using 8,000 time series in each track direction and retrieved, as an example, these two components. So the bottom plot shows the shape of our displacement independent component, and the top plot shows the places where it's active. And here we can see that for the bottom component, between the 2017 eruption at Fernandina and the 2018 eruption at Fernandina and Sierra Negra, we retrieve active independent components at both of those volcanoes, as well as slightly at Cervosol. And then prior to the 2022 eruption at Wolf, we see we retrieve independent component at Wolf, Fernandina, Sierra Negra, and then a little bit at Cervosol. Again, suggesting that our periods of heightened correlation are occurring when there's heightened magma flux, so during eruptions or during the pre-eruptive accumulation of magma. And this is consistent, I think anyway, with what we know about Galápagos volcanism. Magma supply there is not linear with time. It's been quite dynamic with time. Eruptions have, in the last 20 years, occurred somewhat in clusters. So from 1993 to 1998, there were 4 eruptions. There were then no eruptions until 2005, when there were another 4 eruptions. There was nothing then from 2008 to 2015. Since then, there has been 6 eruptions. Even if we consider the uplift at Sierra Negra, which again is like famously quite high. As Julia said the other day, it accounted for 38% of the detections in her INSAR algorithm. Even that consists of at least 4 subphases of uplift, again suggesting that the uplift rate there is not linear and that magma supply there is indeed not linear. Volcanoes in the Galápagos periodically resurge. So Alcedo, which has been typically undergoing long-term crystallization, in 2006, it resurged for 4 years. There was magma constantly intruding into its subvolcanic reservoir, which then stopped during the 2009 eruption of Fernandina. Finally, magma flushing through the subvolcanic system of at least Fernandina and Wolf drives eruptions in the Galápagos. Most of the magmas that have erupted there have been quite primitive, that flushed through from depth, with less than 10% of the eruptive products being evolved. So knowing all this about the temporal irregularity of supply to the shallow crust, and knowing that we see correlations when there's been a heightened amount of magma supply, we suggest the following conceptual models for what is causing our correlations. When we see positively correlated uplift, so when two shallow reservoirs uplift at the same time, it's due, we think anyway, to a bottom-up supply of magma that affects these neighboring volcanoes at the same time, because fundamentally they're all supplied by the Galápagos plume. During periods of positively correlated subsidence, this supply rate decreases and allows processes such as cooling crystallization to dominate, resulting in simultaneous subsidence. During eruptions, we may get negatively correlated displacement. So when one volcano inflates as another deflates, and then if there's been a change of partitioning, we may see again negatively correlated displacement as magma, which was previously supplied to one, gets rerouted to another. So in summary, volcanic deformation is the shallowest expression of an extensive magmatic system. All major Galápagos volcanoes have had episodes of correlated deformation over the previous 16 years, I guess 17 now actually. These occur during periods of heightened volcanic activity, and we suggest that periodic magma flux from the Galápagos plume into neighboring volcanic systems has been causing correlated deformation. Why is this happening in the Galápagos? We think that it's quite a good place because we have a high number of subaerial volcanoes. We have 6 that regularly form and 7 that are actually there, and we have quite thin crust, so from 12 kilometers at Fernandina up to 18 kilometers at Sierra Negra, which is really good if you can test these correlations, because there's lots of volcanoes to test against, but also there's not much chance for magma to magma upwelling through the crust into the shallow systems is quite rapid and quite obvious. However, there's also evidence of this at other oceanic hotspots. So at Hawaii, for example, there's evidence there since the early 2000s that both Kilauea and Mauna Loa have been undergoing shared or correlated deformation. And this is again kind of anecdotally observed during the most recent eruption at Mauna Loa, when both it and Kilauea stopped erupting at the same time. And that's it. Thank you.